Okay, so in this video we will introduce the concepts of the normal tangential coordinate frame. So we'll talk about normal tangential coordinate frame. Okay. This type of a reference frame is also quite useful in solving problems in dynamics, of course in rigid body dynamics as well. So we will talk about the features of normal tangential coordinate frame. In the process you will see how the normal tangential coordinate frame is different from the other type of coordinate frame that we have used, namely the polar coordinates or the r theta coordinate frames. So let us, to define this normal tangential coordinate frame, let's draw a diagram. So let's say that there is this XYZ fixed reference frame. So this is a fixed coordinate frame, and assume that there is a particle that takes a curved path. Let's say it takes some curved path like this. So the particle is at a certain instant, it is here, then the particle reaches this point, so it is traversing the path in this direction, this point, and then the particle reaches let's say somewhere over here. Now one thing that you can see is that when the particle is here and it is traversing this trajectory, it's got a velocity like this, right? When the particle is here, its velocity is like that, and when the particle is here, its velocity is like this. So this is the velocity, and of course the velocity can change. So these are velocity vectors at different locations as the particle traverses this trajectory. Now one thing that we note here is that a particle's velocity is always tangential to its path, right? So a particle's velocity is tangential to its path, and this is a pretty fundamental observation, pretty basic observation. Now in the NT coordinate system, what we do is the following. We say that we call this direction the direction of the velocity of the particle, which is, by the way, tangential to the path at a certain instant. We call that direction, or the unit vector in that direction, is called E sub t. So t stands for tangential here. Then what we do is we note that if ET is tangential to this path, then perpendicular to that is going to be a direction which will be pointing towards the center of curvature of the path, right? Because the center of curvature is always perpendicular to the tangent, and ET is the tangent. So let's say that the center of curvature at this point is here, at this instant is here. This is a imaginary point, and the radius of curvature at this point is rho, right? So this and let's say the location of the point is P. So PC is perpendicular to ET, okay, and we then define the normal direction En to be the direction which is perpendicular to ET but pointing towards the center of curvature of the path. Alright, so we have two mutually perpendicular vectors, and so we are in the process of defining a triad, and so the third vector is going to be mutually perpendicular to these two, and so that's going to be a vector that is perpendicular like this, and we call that EB. So this is EB. Okay, here you have En and here you have ET, right? So we note that ET, En, EB forms a triad, and this triad is called the NT coordinate system, or the NT triad, normal tangential triad, NT. Now, one thing to note here is that since ET and En are mutually perpendicular, and EB is mutually perpendicular to both, ET and En is going to form a plane. So you can imagine that there is a, I'm shading it here, so let's say there is a plane that is formed by ET and En. So you can imagine that EB is going to be perpendicular to that plane. Okay, so we make a observation that ET and En form a plane, okay, which is, now this plane, by the way, if you think about it, this plane is tangential to the path. So if let's say the particle is taking some path in the three-dimensional space, this is a three-dimensional space. If the particle is taking a path in the three-dimensional space, this plane found by En and ET is going to be also a plane that is tangential to this three-dimensional path at this instant. So this plane has the characteristic that it is a plane that is tangential to the path that the particle is taking. Okay, so forms these two form a plane which is tangential to the path at any instant. So in other words, as the particle travels, since the curvature of the path is changing and the path is in three dimensions, and it can have curvatures in different directions, so this plane can also change its orientation. It's not a plane that is fixed. Okay, as the path changes, the plane also changes, because the plane always remains tangential to the path, and the path itself is three-dimensional. So for instance, when the particle was here, ET was like this, let's say En was this way, because the center of curvature, let's say, was somewhere over here. Okay, let's say the radius of curvature, we still call it rho. So En is like this, ET is like this, and EB would have been, say, like that. Okay, and then we can again shade this plane formed by ET and En, and that plane is that same plane. It's the tangential plane to the trajectory of the particle. So that plane is tangential to the trajectory of the particle at that instant. Same thing happens over here. Now this plane is named the osculating plane. It changes orientation as it keeps itself tangential to the path at any instant. And we also note that ET stands for tangential, EN is normal, and EB, so let me put the EB over here, EB is called binormal. And so you can see that this naming convention is based on what the orientation of these unit vectors are with respect to the trajectory at any instant. ET is tangential to the trajectory, EN is normal to the trajectory towards the center of curvature, and EB is binormal, meaning that it's normal to both the two unit vectors ET and EN. One thing to note here is that osculating plane changes orientation. Right? So as the particle travels, the osculating plane can change its orientation. We also note that EB is always perpendicular to the osculating plane. Right, and you can see over here EB is perpendicular to the osculating plane simply because EB is binormal. It is normal to both the tangential and the normal vector, and since the osculating plane is the plane formed by ET and EN, so EB is by definition perpendicular to the osculating plane. So this triad ET, EN, and EB. Let me just see one thing. ET, EN, and EB. I should make one correction, and perhaps some of you who are viewing this video may have noticed. You will see over here that the way this coordinate system is defined is that ET cross EN gives me EB, which means that if I curl my fingers from ET to EN, that gives me EB, the direction of EB. And that is the convention for defining the normal tangential coordinate frame. Here, however, if I curl my fingers from ET to EN, EB goes downwards and I have shown it upwards. So I need to change the the direction of EB to maintain the right-handed coordinate system convention. So I would say EB is here. Nevertheless, EB, as we have pointed out over here, EB is always perpendicular to the osculating plane. That is true. EB is also mutually perpendicular to EN and ET. That's true as well. And so this is our coordinate frame. One thing that you can see over here, as the particle traverses from this point to this point, you see the orientation of EN and EN and EB change quite a bit. ET, of course, as per the definition, remains tangential to the velocity of the particle, but En is pointed to the right of the path, and by the time you get to this point, En is pointing to the left of the path. So if you are actually the particle taking this trajectory, when you were here, your En was to your right, and when you are here, the En has gone to the left. And that is because the center of curvature has flipped direction. It was on your right, and then by the time you got here, the center of curvature is to your left, and so En has changed or flipped the direction, and that is actually the reason why EB also flipped its direction. So here ET and En are such that EB is downwards, and here En and ET are such that EB is upwards. So one thing to keep in mind is in defining this NT coordinate system, to keep it right-handed so that all our calculations are accurate, we need to have this definition, and that is ET cross En gives me EB, En cross EB gives me ET, and so on. So this is the right-handed NT system. Right now, one thing that will also come up is that, and we just discussed it, that En can flip its direction from right of the curve to left of the curve. So En can flip from right of curve to left, and that happens. And when does that happen? That happens when the curvature changes. So here the curvature is directed, the center of curvature is directed to the right. Here the center of curvature is directed to the left of the path. So when that flip happens, then En will also flip from right to left. Now, since the curvature is to the right over here, and here the curvature is to the left of the path, you may be wondering if at some point the curvature becomes zero, that is, the path has a zero curvature, and that indeed is going to happen. So when the center of curvature flips from one side to the other, there is definitely a point, at least one point in between the two, where the curvature has become equal to zero. So you do have a case where the curvature is zero, and at that point basically the center of curvature becomes at infinity, and at that point, you know, it's a little bit of a special case as to how you define the NT coordinate system, and we'll show that in a second. So En can flip from right of curve to left. So if or when the curvature is zero, okay, which means rho goes to infinity, radius of curvature goes to infinity, in that case En can be defined on either side of the path. Okay, so in that case, En can be defined on either side, and let me just show that with a very simple example. So for instance, let's say the path has a curvature like this, and it changes to a curvature like that. So there is a point where the curvature is zero, and at that point basically this is ET. There is no ambiguity about ET if the particle is going in this direction. So now En, because the curvature is zero, so the radius of curvature is infinity, so rho goes to infinity, and you can draw basically the radius of curvature in either direction because rho is infinity, and so you could have your En pointing this way, or you could have your En pointing that way. Okay, in each case EB is going to be either pointing inwards or it's going to be pointing outwards, depending on what makes the coordinate system a right-handed coordinate system. So if En was here, EB would be, En was pointing in this direction, which is to the right of the trajectory that the particle is taking, then ET cross En would be downwards, so EB would be pointing downwards. On the other hand, if you considered En to be on the left of the trajectory, pointing in this direction, then ET cross En would be pointing up, and so EB would be pointing upwards, perpendicular to the surface of this page. This is considering a 2D curve or a planar curve. Okay, now another feature of the normal tangential coordinate frame. So let me keep this diagram in our view. Okay, so another feature of the normal tangential coordinate frame is that the NT frame does not use the particle's position in its definition. So it does not use the particle's position in its definition. So the position does not show up in the definition of this coordinate frame at all. And this is unlike, for example, the polar coordinate frame or the cylindrical coordinate frame or the r-theta coordinate frame, where the position is used as a starting point to find out the velocities and then the acceleration. So we do not use the position, and so what that means is that the position of the particle cannot be readily expressed using the NT system. And while this may sound like a handicap, it is usually not the case, because the NT system is usually chosen when the direction of the velocity is clear in a problem. You are more interested in finding the accelerations and thereby relating them to forces. When you are interested in doing a velocity analysis, and there are numerous problems where such an analysis, the emphasis on velocity and acceleration is more important, and so the NT frame is very, very useful in that sense. It's usually not a handicap once you have chosen the NT frame and based on the type of analysis that you are planning to do. So how do we start doing analysis? Well, we say that the velocity of the particles, if you focus on this part here where the particle is moving along this curved path, velocity is tangential. So the velocity, and let's say this point is P, this point is P as well. So Vp is nothing but Vet. So there is a very simple formulation of the velocity of the particle, and it's simply that the particle's velocity is whatever the magnitude is v along the et direction, which is the tangential direction. So we start off with this. As you can see, right away we start off with the velocity and not with the position. Okay, so this is the starting point. Next, what we do is we find the angular velocity. So the question is then, what is the acceleration of the point P? Well, all we need to do is carry out derivative of the velocity to find this acceleration. So we can say AP is equal to v dot et plus vet dot. Note that this is indeed, this nt coordinate frame is indeed a rotating coordinate frame, because as the particle goes along a trajectory, you can see that the orientation of the nt frame changes as the particle takes different points along a trajectory, a three-dimensional trajectory. The nt coordinate frame, it changes its orientation. So therefore we need to do a et dot. So this is one of the different types of rotating coordinate frames that we use in solving problems in dynamics. So then the question is, how do we find et dot? Well, et dot is going to be omega cross et, where omega is the net angular velocity of the nt frame. Okay, so and that is actually quite easy to formulate. So let's say that this is again our x, y, z fixed frames, and here is the trajectory of a particle, and at a certain point here the velocity is like that. So velocity is here, et is along the velocity. This is the center of curvature, this is the radius of curvature, en is like that, and eb goes like this. So et, en forms the osculating plane. Now, since the osculating plane is tangential to the trajectory of the particle, you can see that the whole coordinate system, the nt coordinate system, is actually at any instant turning about EB. So this is the direction of omega. So the angular velocity of the nt coordinate frame is at any instant about EB. And what is that angular velocity? Well, you can now predict, because if the velocity of the particle is v and the radius of curvature is rho, then the angular velocity is v divided by rho, right? Because by definition this distance p to c is the radius of curvature. So you can imagine that at this instant the particle is undergoing an infinitesimally small circle of radius rho about the point C, right? So then velocity divided by the radius rho is the angular velocity, and that angular velocity is perpendicular to the et and en vectors. So it is basically perpendicular to the osculating plane, so it is in the EB direction. right? So this is the angular velocity, and so therefore et dot is equal to omega cross et, the basic definition of the rate of change of a unit vector. And so it is v over rho eb cross et. Now our right-handed coordinate frame says that eb cross et is en, so this is v over rho en, right? So therefore the acceleration of the point P is given by v dot et plus v times et dot, so it is v squared over rho en. Right? And this leads to a very interesting observation which goes even beyond just NT coordinate frames. This gives us an insight into the nature of a particle's motion, any particle's motion, any point's motion. Doesn't have to have a mass, even it could be a massless particle, theoretically. But any particle which is going in a curved path, what we are noticing from here is that the acceleration of the particle does have a component which is directed towards the instantaneous center of curvature. So as a particle goes in a curved path, its acceleration consists of two components. One is along the tangential direction, and that acceleration depends on how the velocity itself is changing with time. There is another component of the acceleration of the particle, and that component of the acceleration is towards that instantaneous center. And that acceleration is given by v squared divided by radius of curvature of that curve at that instant. So any particle which is going in a circle or a circular path or a curved path must have an acceleration to the center of that curve at any given instant. And that is a very important insight. It tells us that if a particle, even if the particle is going in a constant velocity along a curve, that particle has an acceleration towards the center of the curve. Okay, so the observation is that a particle moving along a curved trajectory has an instantaneous acceleration towards the instantaneous center of curvature of the path, of the trajectory. Now this acceleration is called the centripetal acceleration. Okay, so the normal tangential coordinate frame brings up another very important feature of a particle's motion, and that is the centripetal acceleration that shows up in a particle whenever a particle is going in a curved path. Okay, and by the way, we should keep in mind that even if v is constant, i.e. v dot is equal to 0, then a of p, that is the acceleration of p, is still going to be v squared over rho en. what that tells us is that it doesn't matter if the particle has a constant velocity or if the velocity is changing, right? As long as it is going in a curved path, okay, it does have an acceleration towards the center of curvature of the path, okay? These are some of the salient features of the NT-coordinate system. It is a very useful coordinate system and can be used to solve a variety of different kinds of problems. So that's it for this video.